that's what I mean, like you get like subliminal
Everyone's
messaging.
happy until it is.
We're honest with each other because we're women and we understand each other.
Okay, I'm going to start by
There's a reason some women become lesbians.
finishing. I want to go through a little bit more on this entity server component and using entities, mostly because that's what you're going to be doing with the next computer assignment. So there are just a couple of points about working with these. Okay, so this is the component, and this uses this transient entity called entity, and this is a simplified class diagram with some of the key elements of it. Really the main one is the timestamp. So the idea is that at certain events you can stamp the time, meaning, and what that means is that the timestamp variable is set to the current value of simulated time. And that's how you remember when that particular entity arrived at some event. And as we will see, and as we have seen, and we'll see again, that if one of these entity objects appears in one of the events, and there are two ways that that can happen, we'll talk about that in a moment, then, if you stamp the time at a particular event, then that remembers when that entity was at that event. I mean, that's a little bit inaccurate, but when that event occurred, that entity happened to be around. And then the second key element of that is this elapsed time, which is the time between the current simulated time and when it was time-stamped. Now, looking at the entity server component, which is yet another multiple server queue, most of this is pretty much the same, except for the parts that deal with the container of entities. So in this case, the arrival event has an argument, which is going to be an entity. And what it does is, the thing you do is you stamp the time of the entity, and that means that that entity object remembers when it arrived. How? I mean, it's not magic. I mean, it basically, the timestamp variable in this entity is set to whatever the sim time of when this arrival event occurred, and that entity was the argument. And then when we add it to the queue, hopefully you can picture now, instead of representing the queue as just a count in which we don't identify the individual customers, here each individual customer is represented by an entity object. And so if there are 5 in the queue, there are 5 entity objects in that queue container, which you can think of as a sorted set. And the sort is by the timestamp. And that's why you have to be a little bit careful. You need to make sure that you stamp the time before you put it on one of these sorted set containers. And that's just a property of how the sorted sets work in Java. And then when the start service event occurs, that entity is popped off the queue. And again, we're using pop because that's the traditional way of removing the first element in one of these data structures. Java, in their infinite wisdom, did not call it pop. In fact, they don't even have a method where in the sorted set interface where you can just sort of remove that first guy, you have to do a little two-step thing. But conceptually, it's a pop. And so at that start service event, this entity that just came off of that queue container remembered when they arrived. Remember, and when did they arrive? That entity arrived at the time it was an argument to the arrival event. So these entities are a second way that you can remember things about the state of the system at one time, that is during one event, and remember them for some later event. In this particular time, D, the delay in the queue, is simply the elapsed time for that entity that just got taken off the queue. And what's that elapsed time? It's the difference between the sim time when the start service event occurred and the time when that entity had been an argument in the arrival event. That is, the difference between the time when that customer started service and when they arrived. And if you think back to the first assignment, that's what you did to compute the delay in the queue. You said this first guy showed up at this time, they started service at that time. Here, we remember when the customer showed up, and then when we start service, we say that difference in time is going to be how long they were in the queue. And that time could be zero. So for example, the very first guy to show up is always going to be able to start service right away. So the start service event is going to be scheduled with a zero delay, which means that for that very first guy, the time in the elapsed time is going to be zero, because the sim time at which the start service event occurred was exactly the same as when the arrival was. For subsequent customers, there's going to be a difference. The second thing is that now syntactically, this customer E is a local variable. And so just like methods, events can have local variables just as a convenience, and in this case it's a little more than a convenience, but that, because that event knows what that variable E is. How does it know it? Because it just removes it from the queue. And so because it knows that, it can pass it to the end service event, and the end service event needs to have that passed to it because the end service event with an argument of an entity means that this is the end service of the customer who just started service. In other words, it's this guy. So unlike the previous models where we did not identify the individual customers, here we do, and that is the only reason that's necessary is because that's the only way we can compute the time in the system for that entity E. And what's the time in the system? Well, again, the elapsed time, because the time hasn't been restamped. It could be. There are situations in which you might want to restamp it. We will actually encounter some, but not yet. But what's the elapsed time between when this entity showed up at the end service event? Well, that's the time between the current time and the time at which that entity showed up at the arrival event. Okay, so moving to again, just kind of looking at how the code works. Where is the entity server? So as you can see that you need to be a little careful when you're importing these, because entity is a very popular name. And so you want the SimKit entity, not one of the other entities. Again, all the rules for a SimKit model are in effect. So parameters are declared to be private and have setters and getters. State variables are declared to be protected and only have getters. And I want to emphasize again, the getter for a state variable that's a container. In fact, in general, when you have getter methods for containers, just like the same principle holds as for arrays. When you have a getter for an array, in 99.9% of the cases you want to return a clone rather than the array itself. Otherwise, it breaks encapsulation. Likewise here, you want to return a copy of the Q container, not the container itself. Now, in this case, it's a shallow copy. You could return a deep copy. That wouldn't be the worst thing in the world. One could argue that a shallow copy still potentially breaks encapsulation because somebody could get that and muck with the contents of that, and that is true. So strictly speaking, a deep copy would be a tighter lock on encapsulation, but in practice, a shallow copy is usually good enough because the thing is we're not living here in a hostile environment where somebody's trying to mess with you. We're living in an environment where it's possible to kind of mess things up. And so you want to protect yourself from yourself. But this, at least returning a copy is important. And unfortunately, the containers do have a clone method, but for some reason, they didn't incorporate the clone method when they implemented the generic. So the clone method in Java objects returns a thing of type object, and so if you clone it, you have to cast it to whatever type you want. If that's your preference, then there's nothing wrong with that. It's just that I just found this to be a little more convenient. Okay, but that's an important thing to do when you have state variables that are containers. Just as when you have state variables that are arrays, the getter returns a clone. Now, the other thing is that you may have been wondering about this, why we have this reset method and run and why that's all separated. That will come into play when we start doing multiple replications of these models. The idea is that when you are doing multiple replications of a simulation under the same conditions, that is, you're not changing the values of the parameters, then each time you run it, this reset method gets called by the schedule reset method, and that guarantees that every simulation component is going to begin the simulation with all of their state variables in their initial values, and that's important. At the end of a run, your states are going to be in whatever they are. So at the end of one of these runs, you might have a bunch of entities sitting around in the queue. If you didn't clear the queue on the next replication, then those entities are still going to be hanging around. And you would begin the next replication with a bunch of guys already in the queue, and that's not what the model says you're supposed to do. You're supposed to begin with nobody in the queue. So that's why this reset method is around. And the other thing is that once we've instantiated this container, we don't want to have to keep reinstantiating it. So we want to be guaranteed that it will be that it'll be around. Otherwise, we're going to get the beloved null pointer exception. So how can we guarantee that? Well, the best guarantee is to actually instantiate it in the zero argument constructor. Why? Because that way, whether we instantiate it with a zero argument constructor or the master constructor, then it will be instantiated and we won't get null pointer exceptions. So how can we guarantee that this will be executed if we use the master constructor? We call this. Okay, so this is the pattern whenever you have containers as state variables. In, again, 99.9% of the cases, instantiate it in the zero argument constructor and be sure to call this from the master constructor.
Why is it that way?
Why
why we have a separate no argument constructor for just the container variables?
Well, the zero argument constructor comes into play when we're instantiating these components from an input file. And
Yeah,
so,
that makes sense, yeah.
so typically there you'll have data that comes in. All data is essentially strings. And so if I have a string, but in this particular case I need to know say the total number of servers. So I get a string that will parse to an int. So if I'm writing a method that will, if I'm writing code that will take an input file and turn it into one of these, what I can do is if I get the name of the class, then I can use reflection to instantiate it with the zero argument constructor, and then I can use inspection on that class that I've then created to determine that this state variable, the total number of servers, is in fact an int, and so I need to parse the string that I've just gotten from my data file into an int. Whereas if it were something else, like a double, or in this case a random variate, I would need to take that and parse it into a random variate. So the idea is that whereas here, if I try to use the master constructor, I need more information about the class. I need to hardwire more information about the class into my builder. This way I can write code that will instantiate any one of these from any data file as long as it has the right information. Okay, so be sure to stamp the time before you put it into before you add it to the queue. The other thing is that because Java doesn't have the pop, we have to do kind of a little dance, and again, it's worth taking a look at what this does. In other words, the same old value, new value business kind of holds. See here, this is important because this will return a copy of the old queue, and then when you fire the property change, it will actually create another copy, and that may seem a little bit wasteful, but it preserves the integrity of the whole thing. So it's a bit of a trade-off. And again, because they don't have a pop, we have to actually first get a reference to that first guy and then explicitly remove him. These two calls together implement the pop thing. Now, just all of this should be relatively familiar, except for I just wanted to point out a couple of additional classes here that you will be using. One is this collection size time varying stats, which operates the same way as a property change listener, where the argument is the name of the property that it's listening to. So this name has to match this property change. And what the collection size does is it's a time varying stat of the size of the collection, because if we're asking if we're trying to estimate the utilization, in this case, not the utilization, the average number in the queue. The average number in the queue is going to be a time-varying average of the size of that container. Whereas the container itself, if we were to try to figure that out from the container itself, what we would get is we would get a pile of entities, and that's not terribly useful. The other is that for the tally stats, there's a simple stats tally. And for the delay in the queue and the time in the system, we tally those because those are discrete observations, just think back to the first assignment, where we tallied the delay in the queue by saying the first customer had this, the second customer had that, etc. And likewise, the time in the system, first customer had this time, second customer had that time, etc. So that's how it does it. Everything else is fairly straightforward. Oh yeah, one more little thing. To compute the arrival rate, just as you did in the assignment, it would be the number of arrivals divided by the time. So how do we get the time? Well, the schedule class had the event list has something called sim time, and it has a getter. We say get the sim time. Now, how can we count the number of arrivals? You may or may not have noticed that the entity server did not have a state that counted the number of service completions, for example. Well, one at least estimate of that is we can get the total number of arrivals from the entity arrival process. What else was using Little's formula, you take the number in the queue, the average number in the queue divided by the arrival rate, and by Little's formula, that should give us an estimate of the delay in the queue, again, using Little's formula, and that's what we print out here. Okay, now that he's gone, I can speak freely. No. Okay. Okay, so that's, now, let's,
Will be in the repository, right? Or that code will be in GitLab?
it is. If you do a pull, it's there.
Okay, thank you.
Yeah, all that code is in GitLab. Okay, so now let's a model for reneging, which we've already kind of done. So now the entity server was our basic multiple server queue. But now we want to model the situation with reneging customers, because that's really the most, a little bit more complicated. One of the reasons I like this is that there are some other, in some of the commercial packages, they have a different way of modeling this kind of thing, and they have a real hard time modeling reneges typically. Whereas here, I hope you can see that it's fairly easy, fairly straightforward. So we'll do that, and then time permitting, I want to be a little bit more explicit in presenting to you some things about how SimKit is working. Okay, so our queue with reneging customers, again, they're impatient. They arrive to a multiple server queue, and each customer is only willing to wait a certain amount of time. And after that, they're going to renege, leaving the queue. And the measures that we're interested in addition to the usual, the usual suspects are things like the average number in the queue, average delay in queue, average number in system, et cetera, et cetera. But here, in addition to those, we are interested in these 4 measures. First, the percentage of lost customers. That's something that we are interested in as a measure of the impact that our serviceability is having on things. There are, we've been talking about sort of customers and stuff like that, but I think if you think about it, there are situations in which there are time-constrained things going on where if time is up, then things kind of go awry. So your customers might be contacts that you're that you're sensing somehow, and that they are going to maybe leave after a while. What does leaving mean? Means you can't see them anymore. So this model out of the box might not necessarily capture things like that, but the same concept will. In other words, things where you maybe you're tracking a target and need to have take some kind of countermeasure against it, but you can only do the countermeasure if you have eyes on it. And if you lose the eyes on it, then the countermeasure isn't going to work. Now, I mean, obviously there are systems where that isn't necessarily the case, but there are systems where that is the case. So, in other words, this type of model does have applications beyond just sort of losing customers. But nevertheless, if I'm running this facility, I want to, how many customers am I losing? And what can I do about that? What you can do is maybe hire another server. And that's a question that could be asked. But then you might be interested in what is the average time in the queue for the customers who left versus the time in the queue for the customers who were served, or the time in the system for the customers who were served. And the reason that's it's important to distinguish those questions is because how much time in the system did a customer who reneged spend? Well, technically they were just kind of in the queue, but if you were to include those observations in the time in the system, it would seem like your customers were spending much less time than they were. In other words, I'm kind of more interested in the time in the system for the guys who were served than the ones who left, because the ones who left didn't spend as much time in the system as the ones who actually got served, typically. Okay, so now the way that this is going to be done, again, there are always different ways of doing this, but this is the way that we're going to do it, and this is the way I'm going to ask you to do it. So now what we're going to do is we're going to move the service time from the server into the customer. And we're also going to have the customer hold their renege time. So both of those values were in the server in our previous model, and we're now going to move those into the entity. What that actually does, I mean, even though for this model it isn't necessarily going to kind of come up, but what this gives us is the capability to do is to have multiple types of servers with maybe different service time requirements, and maybe different types of customers with different levels of impatience. In other words, we could, because that's a function of creating the customers, the same server component is going to be able to exist and serve different types of these things. Now, for this model, we're just going to have the one. And so what we're going to do, and then in the implementation, conceptually, we have a subclass of the entity class. So in the abstract, we're adding two attributes, that is two instance variables that are going to be the service time and the renege time, and then we have getters for each one. And then how do we get them in there? Well, we're not going to have setters in this case, but we're going to have to pass them through the constructor. So we're going to tell the customer, this is your service time, this is your renege time, and then that's what they're going to have. Okay, so from an event graph perspective, we're set. In Java, then we would simply subclass the entity class. And that's by the way, what I'm going to ask you to do. But in order to create these, we need a component to do that, and we can follow the same pattern that we've had before. We can take our friend, the arrival process, that produces the sequence of arrival events, and using the virtue of laziness, we can simply reuse that, as it were. But now our subclass needs to have two parameters. One is the sequence of service times, and the other is the sequence of renege times. These were both parameters that were in the previous model, but now we're moving them into this customer arrival process model component. Okay, so these were in the server piece, and now they're going to be in the arrival process piece. And they show up right here. So the arrival event will instantiate a new customer, passing it the service time and the renege time. So each customer will come in carrying around its service time and its renege time. So now our server component is left with just one single parameter, just the total number of servers. Because all the other ones are we've shoved them all into the arrival process now. In addition to the inter-arrival times, it has the service time sequence and the renege time sequence. Our state variables now are pretty much almost the same as before. So the number of available servers, the number of reneges, which is going to initially be, okay, I should have done this. This should be 0. The delay in the queue for the reneges, the delay in queue for served, and the time in the system for those served. So this is the same as before, except that the sorted container now contains these customer guys instead of the integer IDs that we had in the previous model. And so here's what it looks like. And again, why does it keep making my pointer disappear? Come on. Yeah.
Adds a more artistic.
Oh, yeah. It does, yes. These infernal contraptions are colored. Okay. All right. So again, we see in the top part a pattern that should look very familiar. You know, this is our arrival. This is our server parameter. Server component, you know. But what we've added was just as before, we've added the renege event, and then the same pattern here. So now our arrival is going to be one of these customers. And just as with the entity server, we're going to stamp the time and add it to the queue. So that's the same as before, except that in the entity server, we were doing it to entities. Here we're doing it to customers, which are a subclass of entities. And again, if what it does is two things. It schedules the renege. So if that renege event happens to happen first, then the guy gets removed from the queue. And if a server is available, we'll schedule a start service right away. Now, here's where we are using the attributes of the customer. So here, before, this component had that sequence of renege times as its parameter, but now it gets it from the customer. So here when it says C dot, I mean, here it's, technically speaking, we're pretending that this attribute is somehow a public thing that we can just directly access. In fact, what we're doing is we're just using a shorthand for this. So in the code, you would use a getter. But this, what's key here is that now this component has the ability to be, it's indifferent to how these customers are being modeled with respect to both their service times and with respect to their renege times. In other words, this can handle a heterogeneous collection of these customers because it doesn't know or care how these customers were created using this. All it cares about is that you have a renege time. I'm going to use that renege time and schedule my renege event. So this customer is this impatient. As before, we're going to pop this guy, we're going to pop the first guy off and then cancel the renege event for that customer. So we pass it as an argument on the canceling edge. So that's the other little feature in what I'm going to ask you to do in the implementation is that how do we implement this canceling edge? It's a call called interrupt. So when the renege event occurs, again, we have one more renege event. We make sure we remove that guy from the queue. How do we know which guy to remove? You tell it. That's the argument. And then now we can find the delay in the queue for the customer who reneged because that's simply the elapsed time of the guy who reneged. So this little pattern here is a useful one. In other words, it's similar to the example that I gave several classes ago about, say, firing a missile and then maybe intercepting it. So here you can think of this as that we're firing a missile. This might be the impact event, but this would be the countermeasure event that's successful, and then that cancels the impact event. So it's kind of like that, same pattern. Okay, so the rest of it is pretty much the same as the previous one, with the difference that now we can compute things like the delay in the queue for those reneged. We can compute the delay in the queue for those who got service and the total time in the system for those who got service. And in the previous model where all we had were the IDs, we couldn't do that because the ID didn't carry around the information about when that customer arrived. It just had the identity. Whereas these entity objects can contain, well, they among other things, they do have a unique ID, although we typically don't use that. They do carry around their timestamp, which is the biggest one that we will use generically. But in this case, we also added two more attributes, the service time and the renege time. And you can add whatever extra things that you want to that. So for example, in some of the models that I'm doing for NavSup, I have entity objects there that represent the NINs that they have, and there's a lot of extra information contained in those. You know, things like shelf life and well, just a ton of information, and it just kind of goes into these entity objects. So if I have an entity object, it will represent one of these NINs, and I can query it to get information about it. Okay, so just in the last few minutes, you know, just to kind of put a stake in the ground for this, I've asked you to do a couple of these SimKit models, and in the handouts for those, I've more or less had what I think is sufficient information to do it, but I want to just kind of be a little more explicit about it. And if you look at section 8 of the reading, there's a bit more about that. But actually, one of the most important things there is on the very first page of section 8, is a table which is kind of like a Rosetta Stone between event graphs and the SimKit model. So if you have an event graph, then you can just directly translate it into a SimKit model, and that's your mileage may vary, but at least I find that much easier than coding. So programming is when you know, programming is a challenging activity. Translating from an event graph model into a SimKit model is actually almost a mindless activity. Not too mindless, don't be. Okay, so parameters, you know, we've talked about event graph components have parameters and state variables. So in a SimKit model, we declare the parameters to be private, and they have both setter and getter methods. If we have an array, it should return a clone. If it's a container, as we've seen, it should return a copy. Because Java does not have a richer set of types, for example, it would be nice if it had a type that was a non-negative integer. It doesn't. So if I have an int, as we have, for example, in the total number of servers, then it is possible to set the total number of servers to be -3. And what the heck does it mean to have -3 servers? I mean, that's meaningless. The number of servers must be positive for anything to happen. How would a server component act if I set the total number of servers to 0? What would happen? Yeah, nothing. Nobody would ever get served, because as the customer showed up, remember the first test is S bigger than 0? So if I set K, the total number of servers, to 0, the initial value of the number of available servers is 0, and obviously if I have no servers, I can't have any more available servers than I have servers, and what that means is people will show up to the queue and never leave. You know, so that'll be a Hotel California model. So what you should do then is you should protect your parameters with illegal argument exceptions, meaning if I try to set a server component with, say, 0 or a negative number of total servers, I don't want to, the model, there's no point in running the model. So at the very least, I should throw an illegal argument exception, say, no, you're not going to run this model with that value. Now, state variables should be declared to be protected, and why protected? Mostly so that we've seen how you can subclass one of these components. You generally don't want to go overboard with that, but we've seen some examples where that's a useful thing. And so if the subclass, sometimes you want the subclass to have direct access to those state variables. That's why they need to be protected. If they're private, you can't do that. And they should have a getter method but no setter method. And the reason for that is that the value of a state variable is only a function of its initial value and whatever state transitions have occurred in the simulation. So at any point in time in the simulation, that's the only thing that should change the value of a state. Its initial value in the reset method and whatever state transitions the events have occurred. So a setter is just not there. So getters for containers and arrays should return a shallow copy. Again, if you're more tightly, if you want tighter encapsulation, then a deep copy would work, but a shallow copy is generally sufficient. Arrays should return a clone. And then the other thing that we haven't looked at yet, but if I have an array state variable that is, if I have an array state variable, I should have index getters as well, and that's a Java Beans type of thing. And that turns out to be very convenient. Okay, the sim entity base is the main base class. There are actually two base class. There's a base class that's even above that, but and in some cases you might want to kind of use that one. The sim entity base one uses reflection to figure out how to execute events, and if for some reason you don't like that, you can go to the basic sim entity, which is a super class of this, and that does not use reflection, and in that case you have to do everything by hand. We will only be dealing with this one. If anybody's interested in the other thing, I can talk to you offline. Okay, so typically for a sim event graph component, we subclass sim entity base, and this is one of the this is one of the unfortunate early decisions that I made, which is to map the events into these methods that have this do in front of it. If I were writing it today, I would do something a little different. The dilemma was that by the time I realized how that wasn't the best way to do it, there was a ton of code that used that, and so I didn't want to break that. So I'm kind of stuck with it, and it's not the worst thing in the world. But again, if I were doing it today, I'd do it a little different. That's why the Python version has a slightly different approach. Okay, so the one exception to that is the run event. So there's a do run method, but the initializing of the state variables, that is the state transition, is done in the reset method. And there are a couple reasons for that. The main one is to make sure that before the simulation even begins, before a single event gets executed by the event list, that all components have had an opportunity to initialize their state variable. In other words, no event in the simulation should occur when other components have not yet initialized their state variables. And so typically the do run method, though, it will fire the property change events for those initial values. And that's important because that's important for time varying state variables, because you need to have that initial value. And basically in our do methods, we have state transitions and scheduling calls, which are the wait delay statements, and then in addition to that we have canceling edges, which are the interrupt business. The state transitions for time varying state variables is we typically save the old value, we execute the state transition, then we fire the property change. The convention is to always use the getter. It just tends to work out a little bit better that way. For situations where we have containers, then it's actually a little more necessary. For tally state variables like delay in queue and time in system, we will typically initialize those to not a number, because they don't exist until a certain event later occurs. We will there typically is no old value, and so we just fire the state transition with the name and the new value. And the reason for that is because they're a tally, the old value is really irrelevant. If you think about, say, delay in the queue. So a customer shows up, we have the delay in the queue. What's the old value? Well, the old value is the delay in the queue of the previous customer. But that has no relationship to the delay in the queue of this customer, or no concrete one. Whereas the number in the queue, the new value does have a direct relationship. In other words, if I've just had an arrival event, the old value in the queue is one less than the new value is one more than the old value. In other words, they're directly related by numerically. So scheduling, we use wait delay. If there's an edge condition, I wrap it in an if statement. And you may or may not have noticed that the wait delay it's very heavily overloaded in that there are a lot of different options for that. Some of the options are putting a priority on, as we've seen, and the other option that you'll encounter is having an argument on it. So we'll see what that's about. The basic form is the name and the delay. If we have a priority, it's the name, the delay, and the priority. If we just have the name, the delay, without a priority, so we have the name, the delay, and then a list of parameters. And or if we have priority in the parameters, the priority goes between the delay and the parameters. Now, canceling edges, which you're going to encounter tomorrow, is the interrupt. So the basic form is we interrupt and give it the event name. And again, that removes the earliest scheduled event with a given name and 0 arguments. So if we don't give it any arguments, it will try to remove just the event that has no arguments. But if I want to remove one with an argument, and that's what you're going to be doing, is I need to give that argument as in this case, as the second one. And if there are more than one, you can just keep listing them. And that's because it was implemented using varargs. And it just, so if I have interrupt arrival 3, then it will cancel an arrival event that had been scheduled with a value of 3. In other words, the match has to be both with the name and an exact match of the parameter. So in what I'm going to ask you to do, the interrupt will be of a renege event with a particular entity. And so it will only match a renege event that had been scheduled with that exact entity. And because all the arrival events schedule the renege event with the entity that just arrived, that should always be the case.